All right, greetings, math people. Today we're going to be talking about distance and displacement. Let's go ahead and get right into it.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe-to-toe, impeccable, splitting your back, son, simple as addition and subtraction, black thought, the infinite relax one.
Okay, let me begin by just giving a basic definition for distance and displacement. So distance, kind of think of it like a pedometer. It's kind of measuring how many steps you take, regardless of the direction. So we're speaking of distance and displacement here in the context of rectilinear motion. So in the context of a particle or something moving either only horizontally, which we'll describe as left and right, or vertically, which we'll describe as up and down. So in that particular context, the velocity of the particle or whatever is positive when it moves up or to the right and negative when it moves down or to the left. So therefore, moving to the right is a positive direction and moving to the left is a negative direction. The same thing for up and down, respectively. So distance, however, just counts steps. Again, it's your pedometer. It doesn't matter whether you're going right or left or up or down. It's just a step to it. So your pedometer doesn't care what direction you go in. You're just counting the steps in which you're traveling. Whereas displacement, the basic definition of displacement is it's just how far you were displaced. So it's basically the measurement from where you started from to where you ended. That's displacement. Distance is just a total steps taken. Displacement is just the difference from where you started at to where you ended from. So let me try to illustrate this point a little further. So let's mark some points here. So we'll call this 0, and we'll call this 1, and we'll call this 2, and we'll call this -1, and we'll call this -2. And so let's say we have something, say a particle, starting at x equals 1. So we'll call these values x. And let's say our particle moves 1 unit to the right. So it took 1 step. And then let's say it moves 3 units to the left. So it took 1 step, and then it took 3 steps. So it took a total of 4 steps in the context of distance. Again, distance, I don't care about the direction. So my distance in this particular scenario is 4. Took 1 step, then I took 3 steps. That's the distance. But the displacement, how was it displaced? Not how far of a distance did it travel, but how was it displaced? Meaning, what transpired from the beginning point to the ending point? So we started off at 1 and we ended at -1. So we were displaced 2 units to the left. We were displaced 2 units to the left. And for displacement, the value can be negative. Now, distance must be a non-negative number. Displacement could be anything. Because if you're displaced to the left or down, your displacement is negative. And if you're displaced to the right or up, the displacement is positive. And if you end up where you started, of course, the displacement is 0. So in this case, the displacement is -2. Now, another way to think of the distance and the displacement is to think of the signs of how you traveled. So technically, when we move 3 units to the left, that's in the negative direction. So looking at displacement first, if we just add these values, the displacement would be 1 plus -3, giving us that -2. And for the distance, where we don't care about the direction, so we just take the absolute value of everything traveled, it would be the absolute value of 1 plus the absolute value of -3, giving us 4. In fact, that's the best way to think of distance, other than our elementary definition. Distance is just the total units traveled, irregardless of direction. It's also the absolute value of what's traveled. Again, understanding in rectilinear motion, some travel is considered negative, where for displacement, you do not take that absolute value. You just take the values as they are. So let's look at a little example. So let me just set up a scenario. So say I have a projectile shot into the air, shot straight up into the air with the initial velocity of 30 meters per second. And let's say it's shot up in the air from ground level. And so you've learned in pre-calculus and calculus how to write a function modeling that. So our function for this scenario would be y of t is -5 t squared plus 30t. And just to review how we develop position functions for projectile motion, if the units are in meters, then it's just going to be always -5 t squared. That -5 t squared, that -5 comes from half the acceleration due to gravity, which is -9.81 meters per second squared, but we round to -10 for easy mathematics. And then the coefficient of t, that 30 ct, that 30 comes from the initial velocity of the problem, which I stated was 30. And then sometimes there is a constant, which is the initial height. But this one, in this case, I said, just assume we're going from ground level. And so the initial height is 0. So that's why we just have -5 t squared plus 30t. Now that's, of course, called the position function. And the derivative of the position function is the velocity function. So I would like to write the velocity function here. And this, of course, is y prime. And it's -10t plus 30. And that velocity function should make all the common sense in the world, because I'm throwing a projectile up in the air at an initial velocity of 30 meters per second. And the only thing acting on that velocity is the acceleration due to gravity, which is -10 meters per second squared. Again, I'm rounding to -10 meters per second squared, which means every second it's going to take off 10 meters per second. And that's what you see from this position function. You see you have this constant that you started with at 30, and every second, plugging in, when t is 1, it's going to take off 10. When t is 2, it's going to take off 20, etc. So that should make common sense. Now, this velocity is a rate. So this initial position function is measured in meters. This velocity is a rate is measured in meters per second. And of course, if I take the derivative of the velocity, I'll get the acceleration, which will be a constant, which would just give me -10. And that's, again, because the acceleration in this case is gravity, which, again, we have rounded to -10 meters per second squared. But the issue is, what if I wanted to find the displacement or distance of this particular projectile through some particular interval of time? Now, again, when we find distance or displacement, it's on some particular time interval. It's not at an instant, because you don't travel at an instant. So a distance and displacement is going to be from some time interval A to B. And so let's say, and we'll do a couple of these. Let's say I want to find the distance or displacement, I don't know what it will be, from this this projectile from time t equals 1 to time t equals 2. So I want to find that. Now, we understand in calculus the way to go from a rate to a total or a net change or an accumulation. Now, again, I just want to think about this for a second. This velocity is illustrating the amount of meters traveled every second. The amount of meters traveled every second. That's a rate. If I integrate that rate, it's going to give me meters. It's going to give me the amount of meters traveled in a particular interval. And I want to see, how I can integrate that and get distance, and how I can integrate that and get displacement. So let me just integrate this guy. So we're going to integrate v of t, which is negative 10t plus 30 dt. And what do we say? 1 to 2. So we'll integrate from 1 to 2. And so the integral here would be negative 5t squared plus 30t. And I know what you're saying. You're saying that was just y of t. Yes, indeed it was, because when you integrate velocity, you get position. And we're going to evaluate it from 1 to 2. So let's see what happens when we plug in 2. So we plug in 2, that's 4 times negative 5, that's negative 20. And then 2 times 30 is 60, negative 20 and 60 is 40 minus, and if I plug in 1, that'll be just negative 5 and 30, 25. So we get 15. All right, so actually the distance and displacement traveled in this case is 15. Now, let's talk about when distance and displacement is the same. So distance and displacement is the same when the object is traveling in the positive direction and it doesn't change direction. So in this case, from 1 to 2 seconds, this projectile is moving up. So that's a positive direction. And it's not changing direction. So distance and displacement is going to be the same. Now, how do I know that? Well, if I look at this, if I just think about this velocity function here, this function will become 0 when t is 3. Plug in 3 for t, you get 0. And that's when the object reaches its apogee. So it goes up at time t equals 3. It reaches its highest point, and then it starts to go down. So numbers north of 3, the object is going down. Numbers less than 3, the object is going up. And if you just look at it, just think about plugging in any number that's less than 3, any positive number less than 3, the velocity is going to be positive. And when the velocity is positive, you're moving up. And think of plugging in any number greater than 3, this velocity is going to be negative. And when you're negative, you're moving down. So if I'm moving in a positive direction and I'm not changing direction, then distance and displacement will always be the same. So in this case, it wasn't really a whole lot to do. The distance and displacement is the same. So let's look at an interval where the distance and displacement is not. So I mentioned after it hits 3 seconds, it starts to go down. So let's take the same situation and let's integrate it from 2 to 4. So we're part of it. Part of this, it's going up, and that's going from 2 to 3, and the other part is going down from 3 to 4. And let's try to figure out a way to reconcile distance and displacement. All right, so I'm just going to change these guys to 2 and 4. All right, so we're going 2 and 4. I probably could have just left the antiderivative there, so let me write that back. Negative 5t squared plus 30 t. And in this time, we're integrating from 2 to 4. And I think we've already figured out what we get when we plug in 2. I believe we got 40 when we went from 1 to 2 when we plug in 2. So we know when we plug in 2, we're going to get 40. Let's see what we get when we plug in 4. So 4 squared is 16. 16 times negative 5 is negative 90. And 4 times 20, excuse me, negative 5 times 16 is negative 80. Please forgive me, negative 80. And 4 times 30 is 120. So you have negative 80 and 120. That gives you 40. And again, when we plug in 2, we've already calculated we get 40. And so we get 0. Now, we got to think about what is that 0? Is that the distance or is that the displacement? So let's think about this object going up. All right, so just a sketch. So this object goes up. That's 1 second, that's 2 seconds, that's 3 seconds. And then it starts to go down. And since it started from ground level, it'll hit the ground right at 6 seconds. And at time t equals 1, so just to map the heights, and we can figure out the height from this position function from y of t, just plugging in the values for t. So when t is 1, for instance, the height is going to be 25. And when t is 2, the height is going to be 40. And when t is 3, it's going to be 45. And when t is 4, it's going back to 40. And when t is 5, it's back to 25. And then when t is 6, of course, it's 0 because it's right there at the ground again. So this is 2 here. So this is when t is 2, and this is when t is 4. So it starts off at 40, and it ends at 40. So that means this value 0, this is the displacement. It's not the distance because it traveled from 2 to 4, it traveled 5 units up and 5 units down. So the distance traveled was 10, but the displacement was 0. So the question is, well, when I take just the integral of the velocity function, I get displacement. Obvious, you can see that from this. So the question is, well, how do I get distance? It has to involve integrating. I have to integrate that rate, that velocity to get the distance traveled, but how in the world can I get the distance? Now, just remember what we said earlier, that when we get distance, we get the values irregardless of direction. So like from 2 to 4, that's considered positive 5. And from 2 to 3, 2 to 3, that's considered positive 5. And 3 to 4, that's considered negative 5. But not when doing distance. When doing distance, everything is considered positive. So if I want to find the total distance, I'm going to integrate the absolute value of the velocity function. So to find distance, so the integral from 2 to 4, I'm going to integrate the absolute value of this velocity function. Now, so that way may bring another issue. How can we actually integrate the absolute value? Do we just turn the negative 10 to positive 10 and just integrate from there? And that's, of course, an incorrect assessment of the situation as it currently stands. So let me clear some of this away, and then we'll talk about what we need to do. So let's get rid of all this stuff here. All right, so Truth is, integrating the absolute value of a function is pretty difficult to do depending on the function. The easy way to do it is to do it from a graphical standpoint. Truth is, speaking to my AP Calculus students, generally when you have to find total distance of a function, of course you can find total distance using the table or using the graph. But typically when finding it from a function, it tends to be a calculator problem where you just integrate the absolute value on the calculator. Because again, integrating the absolute value of a function is somewhat difficult work. But we can do it just thinking about the graph. So let's think about the graph of negative 10t plus 30. So it's a linear function. So let's make some Cartesian plane here. And in this case, each of these graph lines is not going to represent one. So just keep that in mind. So, excuse me. So the graph is going to have a y-intercept of 30 and an x-intercept of 3. So this is not to scale. And so let's just say this is 30, not negative 30. Let's say this is 30 and this is 3. Now, what happens when you take the absolute value? No part of the graph is going to go below the x-axis because this is the negative area. So what happens is it's going to, instead of continuing going down, which would be the case if this wasn't the absolute value, it's going to start to go back up at the same slope. So it goes up at the same slope. So it's going up at a slope of positive 10. Okay, so if we want to find the integral from 2 to 4, we're going to find area under the curve. Now, when t is 2, this is a little triangle here, and the height of this triangle is 10. Just think here, when t is 2, plug in 2 for t, you get 10. Now, when t is 4, you also get 10. So if you plug in 4 here, you'll get negative 40 plus 30, that's negative 10. The absolute value of negative 10 is 10. So what I have are two triangles that have a base of 1 and a height of 10. Area of a triangle is base times height divided by 2. So the area of each triangle is 5. And so this integral is 5 plus 5, which of course is 10. So that's what we have to do. And so in fact, when I integrate the absolute value of the velocity function, I'm integrating speed. So the absolute value of velocity is what we call speed. So if I want to find displacement, I'm going to integrate my velocity function from A to B. If I want to find distance, I'm going to integrate the absolute value of the velocity function, or integrate the speed function. Now, please understand that the absolute value is inside the integral. There's a difference from integrating the absolute value of the velocity function and taking the absolute value of the integral of the velocity function. So we're not doing that. That's what we're not doing to find distance. So it's a no on this guy. No, sir. So if I want to find distance, I'm going to integrate the absolute value of the velocity function, or integrate the speed function. If I want to find displacement, I'm going to integrate just the velocity function. And there, ladies and gentlemen, is the difference between distance and displacement for rectilinear motion in the calculus world. We hope this was some benefit, and we will see you next time.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.